Hello, everybody. Welcome to the webinar here. Thanks for joining us all today for our webinar titled Are Visual Foundation Models on Par with State of the Art? By way of introduction, Frederick, next slide. By way of introduction, I'm Ulrich, president and co-founder of Encord. I'm joined here today by my colleague Frederick, who is Encord's lead machine learning engineer. Frederick holds a PhD in explainable deep learning and generative models and has published research in several leading AI and computer vision journals. So we're very fortunate to have him here today. Next slide.
Hey.
So our objective for today is to build a zero-shot instance segmentation pipeline using the recently released Grounding-DINO and Segment Anything models, and compare the performance of the combined model with a standard Mask-RCNN model to see if our combination is on par with state of the art. I'll spend about 5 to 7 minutes providing a general overview of recent innovations in AI and computer vision, particularly the proliferation of these visual foundation models, before passing it over to Frederick, who will be doing a live tutorial and a comparison. And we'll finish off with a live Q&A session. Next slide. So as all of you know, the past 6 months have been quite the ride in AI, with large language models taking center stage after the release of ChatGPT in November. But of course, text is not the only interesting data modality out there. And for us computer vision practitioners, it is the release of visual foundation models, or VFMs for short, that gets us really excited. So one of the most interesting recent developments have, of course, been progressing beyond purely generative visual foundation models, best known example being Stable Diffusion, which was released in August of last year, to predictive visual foundation models with the Segment Anything model released by Facebook just a little more than a month ago, which to our knowledge is the first publicly available predictive visual foundation model. So contrary to classic deep learning models, visual foundation models can produce images and now also make predictions or inference based on prompts instead of a learned specification. They've been trained in an unsupervised manner and are more general in nature, but they can be fine-tuned to solve specific business objectives with within different domains and industries, which of course have a large number of use cases and potential applications. But our primary focus for this webinar will be on the Segment Anything model and the impact that it can have on building a better computer vision applications. Next slide. So let's dive into Grounding-DINO and the Segment Anything model. We'll start off with a quick overview of Grounding-DINO and then move on to SAM, and then how we combine the two together to achieve what we think are some great segmentation results. So Grounding-DINO is a combination of DINO, which is a semi-supervised learning model, and what the authors called a grounded pre-training that leverages both visual and textual information. So the model basically takes both images and text as inputs and outputs bounding boxes alongside a similarity score to get from this like DINO closed set detection to open set detection, which is the ability to detect objects that are not present within the training set. This is what is commonly referred to as a zero-shot detection. Next slide. And here is an example of what that looks like in practice. So given an image, in this case, of 2 dogs with a stick, and the corresponding prompt, 2 dogs with a stick, Grounding-DINO creates detections, as you can see in the cutout boxes here on the right-hand side, and highlights the part of the prompt with the highest similarity. So in the example, you can see that the 2 boxes around the dog has a high similarity with the 2 dogs part of the prompt, and the stick cutout box has a high similarity with stick. And now moving on to the Segment Anything model, which of course caused quite a stir when it was released last month. It's been trained on the largest known segmentation data set to date, containing about 11 million images and more than 1.1 billion masks, which is about 6 times larger than the previous largest labeled open source data set. Using this model to perform auto segmentation drastically reduces the previous segmentation bottlenecks of having to draw hundreds of key points to create high quality segmentations, which is why it's so exciting. We've summarized the architecture for you guys in the diagram at the bottom of the slide here, but it basically contains a somewhat heavyweight and also a little bit slow image encoder, which outputs an image embedding that is then queued by a variety of input prompts, which could be key points, boxes, grids, or even text to produce object masks. And Fred will touch on more of that later. Next slide. So one of the main advantages of SAM is that it can be used to aid in more complex domain-specific segmentation tasks. So you can fine-tune it to these, and we've integrated into our platform to help speed up the annotation workflows. And as a quick shameless plug here, we've shown what that looks like in our product. And next slide. I won't spoil too much of Frederick's presentation, but putting these pieces together, the audience will have noticed that the thing that SAM is missing is a way to run a context-free or cold inference. It basically relies on a prompt to produce a result. So we thought to combine Grounding-DINO to make an inference about the candidate bounding box and associate label, and then we can use that bounding box to basically prompt the segment anything model for a segmentation mask, as we've shown in the image here. So seeing this, our initial hypothesis was that leveraging the zero shot capabilities of Grounding-DINO and SAM, we could drastically lower the barriers to entry for building an effective computer vision model by drastically reducing the need for label training data. So of course, the question is our combination here on par with state of the art? And with that, I'll pass it over to Frederick, who will go over our evaluation and our findings. So over to you, Fred.
Cool. Thanks a lot. Yeah, thanks for the tour. So yeah, let's see what we can do with Grounding-DINO and segment anything model in a combination. So basically, what I want to cover now is I thought it might be pretty interesting for you guys to actually see a bit of the code that's revolving around stitching these two models together, see some examples of these things being run, and also like actually comparing against Mask-RCNN. So the steps are going to be, first we're going to try out the Grounding-DINO model in isolation, then we're going to try out SAM, then of course we're going to try to marry them. And finally, we should come up with like a function that we can run over an entire data set to do an instant segmentation task, and then compare it to masked RCNN. Cool. So yeah, let's dive right in. I am sure that most of you guys got all the details from Ulrich's tour, but I just wanted to just recap so everyone is on the same page. So on the right here, you can see basically what we're going to try to build in the end. So what we want to do, excuse me, is we want to take an image and we want to take an ontology or like a description of what are the classes we're trying to detect. Then we're going to try to pass them to Grounding-DINO. And so Grounding-DINO is a visual foundation model. And we like to think about visual foundation models as general models where you design prompts rather than design architectures or specific training algorithms. So here the prompt is going to be the image and obviously the ontology. We're going to get into the details in a bit. Okay, so then the idea is now we get a prediction from Grounding-DINO, which is a bounding box, and it's going to be a class as well. Then we're going to take the bounding box and ask SAM. So this is one of the ways you can prompt this other visual foundation model, SAM, by a bounding box, give it, say, like within this bounding box, what is the most relevant mask? So we're going to take the box, pipe it through SAM, and then we're going to get the mask, and we're going to attach that to the predicted class up here from Grounding-DINO, and then hopefully we have a nicely segmented instance. Okay, so on the left is sort of more of a reference for you guys, so you can, all the stuff I'm going to show, you can also find most of the code in this GitHub repository, and like here's how to install the different dependencies. I should also say that we will share all the resources around this webinar, so that means the slides, and I'm also going to show you a notebook, Colab notebook, and you're going to be able to find everything afterwards as well. So no need to sort of screenshot and try to take notes and all that stuff. Just sit tight and enjoy the ride. All right, so first step is testing Grounding-DINO. So again, the idea is we have an input image. So I chose this very nice image of a cat stepping on another cat. Thought it was pretty cute. And so somehow we want to, with code, load the image. We want to define what is our ontology. So in this case, I just chose like a cat, a dog, and a horse, just to sort of see what's going to come out. And then we want to, of course, load the Grounding-DINO model. And we can very easily do that from Hugging Face. So they already have this published, and it's very easy to download and use. Then finally, want to like execute the model. So use the model, the image, the class descriptions, or the ontology. And then we should get some boxes and some phrases with some probabilities of how likely is each of these boxes to be some sort of object. And you can see the result over here. So passing exactly cat, dog, and horse, we got a bunch of bounding boxes, all with cats. I don't know if you can see the labels. One for each of the cats in the images, in this image. Okay. Yeah, so that is the idea. I'm going to show you quickly how this can actually be done in code. So again, there are like 5 steps. First, we need to get an image. So I chose whatever image. And then there's a convenient little load image function. And then you can get the image and you can plot it. So not much magic there. Then the next step is defining our query or our ontology. So here's the cat, dog, and horse thing I talked about. Then finally here, if you guys want to load Grounding-DINO from Hugging Face, here's the function. You just call it and tell it whether you want it to be on the GPU or the CPU. So for this example, I'm using a Colab notebook with a GPU. That means that it's going to run slightly faster than it will when it's running on the CPU. So these models, both like SAM and Grounding-DINO, they're pretty large, and they use these visual transformers as backbones. And visual transformers are generally pretty slow. So this is something we will sort of encounter once in a while. So let me just execute this. Let's load the model. Hope it works. Always exciting with demo times. All right. And so then the next thing is to actually ask Grounding-DINO to do predictions. And again, we don't need to go over the code. I just thought it would be nice for you guys to be able to come back and then find a function called getGroundingOutputs, where you just give it the model, the image, the description, and then you can get the bounding boxes and the phrases. Okay, so let's run on our cat image. Here we go. Now we can also, something is wrong. I forgot to execute this one. Probably also forgot this one. Let's see. Okay. Let's try again. So let's get the predictions. And now you can see, like, you can actually get like an idea of how slow this thing is. So it takes a while to get the outputs here. So the model is running. And there we go. Should be, I wonder if I'm still on the GPU. It's slower than it used to be. Let me check for a bit. No, it should be okay. Yeah, anyway. Okay, and then finally we can of course plot the bounding boxes and the labels. And there we go. Okay, great. So that was the first step, going from an image and a couple of labels. And then the cool thing here about Grounding-DINO is that you can do this on an open set. And that means that you don't need to have Grounding-DINO being trained on cats and dogs and horses in advance. And the reason why this is the case is because one of the backbones it's using is a text encoder that can translate text into these embeddings. And this encoder was trained on like basically the entire internet. So this guy, the text encoder, it knows a lot of stuff, much more than what is in any of these labeled data sets. And so similar embeddings end up similar words end up similar places in the embedding space, which is why you can also, instead of a dog, you could maybe say a mastiff or whatever type of dog you would like, because these embeddings are going to be similar in embedding space. Okay, cool. So this is a really, really powerful way of finding these bounding boxes. Now the next step is to take SAM and then give it these bounding boxes from Grounding-DINO. But before we do that, I just want to take SAM in isolation and then kind of do the same exercise again. So we load the image, or we did that already. And then we want to prompt SAM with some sort of input. So SAM can be prompted with a variety of things. From what was published with SAM, you can do bounding boxes, you can do individual key points. So you could like add 1 point on the cat, and then it would return you the cat, hopefully. Or you can also, of course, do stuff like you can add a grid of points all over the image, and then it would return you all the relevant objects. In the paper, they also present how you can query it with text, and it's actually very similar to how Grounding-DINO works. Although this part was not published, so we don't have the code for that. That is why one of the reasons why we could do this instead. All right, so for this example, the idea is that we take these bounding boxes. Now I just defined a couple of bounding boxes here. Kind of, I didn't draw them in our annotation tool. I just, eyeballed them. And then I load the SAM model. Again, this is very easy. Not from Hugging Face this time, but Facebook AI has a way of downloading their models. And then we can get some masks based on these bounding boxes that we prompt the model with. All right. So same thing goes here. There are like 5 steps. We define what we're searching for. It's the second step. We did load the image already. So that's the prompt. Then we download and load the model. Then we run the model inference and we display the results. So exact same exercise. So here bounding boxes are defined by XY coordinates. So X, Y in the top left corner and X, Y in the bottom right corner. And we can plot this if we want to see it to make sure that our eyeball exercise was good enough. Then again, here's a function for you guys to load the SAM model if you need it one day. So it's relatively easy. Maybe I should remember this time to actually execute these along the way. Yeah, so that's the image. And here is the model, fingers crossed. So we load the model and we have the model in memory now when this is done. It's pretty huge again, so it might take a while. But this step is, of course, like amortized. It's pretty cheap. Okay, I think this notebook is really having a hard time today. Oh, there we go. Okay, and then finally we can prompt the model with an image, bounding boxes, and the device. And so one thing I do want to mention here is that, as Ulrich also mentioned, the SAM model is composed of basically 2 things. One is an image encoder, which is a huge visual transformer, and it's pretty heavy. So it takes like, on this GPU, probably 2 seconds to embed the image. And then it has a couple of other modules, one for encoding these prompts, so the key points of the bounding boxes, and one for decoding the combination of the prompts and the images. So when I say decoding, I mean taking that thing, embedding whatever it is, and then translating it into a mask. And encoding the image is slow, and you do it like this. So you do SAM model.setImage, then it'll encode the image, and then you can actually reuse it. So let's say you had multiple prompts that you wanted to run on the same image, then it becomes very efficient because the remaining components are super fast. So this model is great for interactive use. For example, when you are labeling. So when you're labeling, you would sort of open the image, right, and you would annotate all the different objects in an image, and all the different annotations would be fast, and you could like pre-embed the image in the background. Okay, so this is getting the same output. Let's see. So the set image was the slowest part, and the rest was fast. And then finally, we can display the image here. There we go. So this was for my custom bounding boxes, and it seems to work very well. So back to the slides. Now the final step here is the wedding time, right? So we want to marry these 2 models. So the idea is the gray box is all the stuff we did with Grounding-DINO, roughly. So we give it the cats and the dogs and the horses. This is going to be our only prompt. except from the image, is of course also an input. But the problem is going to be these classes that we care about, and then the rest is going to be automatic. So Grounding-DINO will predict the boxes, and then we will take these boxes and put them directly into, or well, translate them to another coordinate system because they don't agree completely. I guess that's a part of marriage, right? You need some sort of alignment, I suppose. Then you load the SAM model and you pipe the bounding boxes directly into SAM. Oh, whoa, I'm fast now. Right, and then you can plot the combined thing. So fortunately, this part of the code is extremely simple. So there's some code for plotting, not that interesting. There's some code for translating between different coordinate systems, also not that interesting. And then there's the predict function, which basically loads the image, get the Grounding-DINO outputs, transform the coordinate system, and then finally gets the same output. All right, so let's run this again. Now you can sort of get a feel of what is the running time of this thing. So the models are loaded into memory already. And I should say some of this is also just plotting. Plotting is really, really slow in notebooks. Yeah, but there we go. That is our function. So we just do predict on an image and cats, dogs, and horses. And there we go. We have our instance segmentation model right there in front of us. And so what we did from this point on was that we took this function, so predict, and then we took a couple of data sets and we ran this function where this string or this text prompt was just a concatenation like this one with dots of all the classes we knew in the data set. So we had labels for these data sets and we knew all the classes, of course. And then we could do the exact same exercise for every image, and then we could compare the results. So that's the idea. Right. So let's get to that part. We took two data sets. One is one we call EA Quick Start. EA is an abbreviation of Encord Active, which is an active learning tool that we have developed. It's actually open source at Encord, and it comprises a bunch of data sets. One of them is this Quick Start data set, which is a subset of images and labels from the COCO data set. So similar to this image down here, it's a lot of very sort of common images. So it's basically what the internet is flooded with. And in that sense, it should be a relatively easy data set to do. Then to challenge this new married couple, we also took an AV data set. So this is this Berkeley Deep Drive data set. It comprises 1,000 images, the test set. And there are roughly 13,000 labels or masks. Okay, so it's a bit harder because it's probably not what the internet is flooded with, and it's also a lot of very small objects, as you can see here. Right, so this is basically the setup in terms of data. Now, the setup in terms of evaluation is that we evaluate this instance segmentation task similar to how most of the literature does. So we basically compare the mean average precision. So that is the mean of the average precision over each class in the dataset, and of course the mean average recall as well. And we also look at the class-based average precision and average recall. So just like a brief reminder for you guys, how is it that we calculate these things? So first of all, we need to figure out when I have a label, so that's some sort of mask, and I have a prediction somewhere. When do I consider these two a match? And the first thing we employ is the IOU, or the intersection over union. And that is basically exactly what the name says. So it's the intersection of the two objects, the orange and the green one, divided by the union of the two objects, the size, so the yellow part of the two squares here. And that is an indicator of how well these two match. So then we set some sort of threshold, and the scores we share in these slides are based on a 0.5 IOU threshold. So every label and prediction that has an IOU over 0.5 is considered a match, right? And so when do we consider things to be correct? Well, we could set thresholds for the predicted probabilities of each class in order to select what the classes should be, but we could also look at all of them, and then we could compute a precision recall curve and then compute the area under the curve. So that is what is done in mean average precision. And finally, of course, there are many classes. There's one for dogs, cats, frogs, and horses, and we compute the mean of all of these. All right, so let's get to it. So these are the high-level results that we found. First, so let's just decompose this table. So the first column is, of course, the approach, the Mask-RCNN, first row, and the Grounding-DINO plus SAM in the second. Then the second column is the EA quick start, or the COCO subset data set. And the third column over here is the Berkeley deep drive. And so then we report both the mean average precision and the mean average recall for each of these data sets. And except from mean average recall on the quick start data set, we actually find that Mask-RCNN, it performs better, than Grounding-DINO and SAM. So this, of course, raises the question, how can that be when what we saw on these examples that I showed you previously, they seemed so flawless? And I think the main answer is probably that most images are not as nice as the images we saw. Oh, wait, actually, I forgot to show you one thing. I wanted to show you that I also did this for a couple of other images. So let me just let this run in the background. Then I can show you. You'll be a bit more convinced that this works pretty well. Okay, yeah, so these are the sort of overall results. Grounding-DINO plus SAM does very well in terms of mean average recall on the quick start data set. So that basically means that it finds a lot of objects, of the labeled objects in the data set, while the precision is pretty low. So that means that it predicts a lot of objects that are not actually labeled objects. So this might also hint at something that could be wrong with the data set. All right, let's carry on. So if we look at the BDD data set, and we look on each specific class in the data set, what we see is that when we compare Grounding-DINO and SAM on the left to Mask-RCNN on the right, then on average, as we saw before, Mask-RCNN is just better. And if we compare the classes, so these are ordered by the recall of each of the models. So color codings are the same class. So the car over here is the dark blue, and the car over here is the dark blue. So the best performing class for Mask-RCNN is the car, while it's the pedestrians for Grounding-DINO and SAM. And we can sort of see that for very common objects, it seems like Grounding-DINO is actually doing pretty well. But when it comes to more like objects that you would probably expect would be less likely to be in like on the internet or like in less amounts, then the performance is slightly worse. Yes, okay. So I wanted to show you a little bit of what more we were looking into when we did this experiment. So here I have open Encord Active. So you might call it a shameless plug. I don't know. I think it's pretty powerful. So if I go to the Berkeley deep drive, for example, I can go here and I can have a look at my model performance. So let me choose SAM. And so one of the things we do within Encord Active is that we compute a bunch of quality metrics on the data and on the labels. And these quality metrics are used to decompose model performance. So for example, here, one thing we can see immediately from this page is that object area is something that is super important in terms of model performance for SAM. So it's pretty interesting to actually take a deeper look into that. So let's go to the Explorer and let's see some of the false positives. Oh, wait, actually, I'm going to do one thing first. So I'm going to go to the performance by metric. So to get a deeper understanding of what is it that is wrong with the object area, let me jump to this plot. So, okay, so here I can see the precision of SAM plus Grounding-DINO as a function of the object area. So that's the size of each of the predicted masks. And I can see when the size of the mask is very small, then the precision is horrible. And I can also see that there's a lot of data sitting down here. So it seems like there are a lot of small predictions that just don't match anything in the labeled data set. While as soon as the objects become large enough, then my model actually seems to be performing pretty well. Precision of 0.8, that's actually pretty good. Okay, so let's take a step deeper and let's have a look at some of the false positives and order by the object area. So let's see. Here the object area is low. And you can see this little thing here. It's apparently a prediction. And yeah, that doesn't seem to really be a car. That's not that great. And if I look in the other end, so now I'm going to look at the big objects, then I can start see some other stuff. So here are actually some pretty interesting things. So it seems like SAM and Grounding-DINO, they pick up this front of the car as actually being a car, but it's not labeled in the data set. So this is actually a labeling mistake rather than a model mistake. So these are just some of the things that you can do with Encord Active, and it helps getting a better understanding of what is up and down with the model performance. So one thing we could, for example, do here is we could also sort by, if we want to find label errors specifically, we could also sort by the model confidence. So how confident is Grounding-DINO that whatever it predicted is actually true? And then we could start looking for things that have gone wrong. But it seems like a lot of these are also these very small objects. So that begs another question. Could we just remove all the small predictions and could we then get a better model performance? And we probably could. We didn't take that step, but it would certainly be very interesting to do. Yeah, so that's basically it for what I wanted to show you guys. So basically the main takeaways are that Grounding-DINO and SAM is a really good baseline. You can do a lot of cool stuff, especially on common objects. There is one kind of issue, which is the inference time. It's pretty slow. So waiting 2 seconds for every image is probably not good enough for any production environment. So it's going to be really hard to put it directly into production. We also see a very big variance in terms of different classes and the performance of the model. So very common objects typically seem to perform much better than objects that are less common. Yeah, so that kind of hints at it's limited to what the internet is full of, which is regular images. You can, for example, see, I think now this finished. So these are a bunch of other examples where I ran this combination. So for these very nice images, it works okay. And then when we go to a SAR image, then things start to become a bit more rusty, you may say. So I think for nice images, quote unquote, it works very well. But for more specific types of data, it is slightly less applicable. Yeah. So I promised you a bunch of resources. They are here. There's going to be the notebook that I just showed you. There's also a notebook for actually doing the experiments on these Encord Active projects. So if you have your own Encord project, you could do the same thing if you want to get your own specific results. Yeah, there's also a bunch of resources if you want to know more about these different visual foundation models. Otherwise, back to you, Ulrich.
Yeah, thank you so much, Frederick. That was extremely helpful. And just for the audience, we are going to share the slides along with the Colab notebook after the webinar has ended alongside the recording. So if you want to try it out for yourself, you definitely can. And we will, again, be sharing this information soon after. So moving on to Q&A, we had a few pre-recorded questions from the audience. The first question comes from a geospatial company, and the question is, how robust are these models for geospatial data?
Yeah, that's a great question, and I think I kind of alluded to it already. But for starters, I wouldn't say it's great for these geospatial data data sets or problems, but I think you will be able to fine tune these things. So basically, Grounding-DINO, or grounded, sorry, not grinding, Grounded-DINO was trained based on a bunch of labels to be able to learn how to match images and text. So I think what needs to happen is somehow you need to swap out the image encoder to something that knows SAR, basically SAR data or geospatial data better. And then I think you can actually start doing it pretty well. So I think with fine tuning, I think you can do it, but not out of the box.
Got it. And I guess corresponding questions is for, we have a lot of customers that are working with different types of medical imagery, like CT scans, MRI scans, PET scans. Could you perhaps comment on that as well?
Yeah, definitely. So it actually seems like if you use SAM in isolation, it works very well, even on CT scans and all like various kinds of medical data. But Grounding-DINO doesn't, it seems. So that's, again, a place where you need to figure out a better way to suggest these bounding boxes in the first place. But that said, I think you can, again, like fine tuning is probably the way to go. There's also a pretty big project going on for language models it's called parameter efficient fine tuning. So it's figuring out which parameters in these huge models to fine tune to get the most bang for the bucks. And I am pretty certain that something similar is going to happen for the visual foundation models. Yeah.
Got it. And what do you think that SAM is doing a good job on CT scans, for example? Do you have any hypothesis on that?
I think it's because it's often pretty simple images. They have some pretty well-defined edges and stuff like that. And SAM has been shown to work well on edge detection, for example. So that's probably why. I don't think Grounded-DINO will know how to relate these different objects to bounding boxes. I think that's where the chain is sort of going to jump off, or like, yeah.
Got it. Excellent. And we have two questions around model inference speed. One from a pre-recorded question from a person before the webinar started, which is how do you optimize the model's inference speeds to handle multiple requests in real time? Other question closely related is you mentioned during the presentation here that inference time is 2 seconds per image. There's a question around like what GPU that estimate is on, and could you also talk about like what's causing this inference speed to be so long? Of course, you alluded to it in the demonstration, but yeah, just curious to hear.
Yeah, super exciting questions. So first, let's take one question first. So one is like, how can you optimize this model inference speed on like multiple requests? So I think one thing that is very common when you use GPUs is that you batch things, right? You should never like just run one image through your GPU at once, because it has a huge overhead to spin up all these small processors within the GPU. So what you want to do is you want to batch your data. And the way you do that in production is you typically do something like wait for, say, half a second for every request that comes in and stack these things together. And then when either your batch size is large enough not to be able to fit more into the GPU memory, or when the time is up, then you pipe this particular thing through the GPU or the network, and then you return the results. Like you decompose the batch, basically. So that's one way to fix this issue. And then, of course, when the load gets too big, then you need to replicate at some point. So for the second one, the estimates was, I don't know if we can actually see the view resource, perhaps. No, so I don't think I can see them here. Is there any cool way of doing that? Is there? There we go. Can we see it here? I don't think it's available. Anyway, I think most of the estimates from the SAM paper, at least, they're done on an A100, NVIDIA A100. Yeah.
Got it. And I guess another question that we had beforehand was, what does the release of DINO V2 mean for accuracy and general performance?
Right, that's another great question. Unfortunately, it's not just plug and play to add DINO. I actually added a slide on that because I kind of suspected that it would come up. So this is back to the slide that you showed, Ulrich, with the composition of the Grounding-DINO model, which basically had like this text backbone and it had like this image backbone. And traditionally, this would be DINO that would be sitting here. And now it would be amazing if we could just say, oh, let's swap out DINO with DINO version 2. That would be amazing. But I don't think the embedding space of DINO version 2, it aligns with the embedding space of DINO version 1. So that means that now all the functions that come after this part, so all these things, they need, so the cross-modality decoder, the language-guided query selection, all these things, they need to be retrained or fine-tuned, or it's not clear exactly how to do it, but something needs to be done. So you need to redo training to be able to use DINO V2. But that being said, I think it's probably gonna be better. It would be weird to think otherwise. That being said, the way these things are trained, or this particular model is trained, is still on labeled data. So you have this huge O365, I think it's called, data set, which is full of a lot of labels. And you use these labels to sort of match embeddings from the text backbone and the image backbone. And it's still somewhat going to be limited to these labels you have. So if you don't have new labels from new domains, you won't be able to do significantly better, at least. It's my guess. Like, who knows, right? But that's my best guess.
Got it. And here is actually a question from the audience, which came beforehand. So this is not a shameless plug, but a genuine question: is how SAM is integrated with Encord. So be curious if you could comment on how we've integrated it into like the annotation process, like how does the model work, and just like give a general sense for like how you get this work in production.
Yeah, definitely. So there are, of course, a lot of like technical complications around doing this. One is that SAM might not work for every single modality. So that sort of begs for a way to fine tune it on your specific data. That's one thing. Another thing is it might not work on a specific task. So something that has not really been mentioned in this webinar is that SAM, like, because these prompts are typically ambiguous, which means that if I put one key point on, like say my shirt, right? It's not clear if I mean the shirt. So if I am some sort of fashion company, I might mean the shirt, right? But if I am some sort of CCTV security company, I probably care about the entire person. So it's not clear to SAM from the beginning what I care about. And so then what I can do is I can interact multiple times. So I can click multiple times and say, oh, I care about all these regions of the same object. And of course, that requires a lot of development in terms of interaction, but it also requires, like, if you want to get rid of that interaction and make annotation even faster and more automated, you need to be able to disambiguate these things. And you can also do that by fine tuning. So that's one thing. Another thing is, of course, this thing we talked about with the image encoder, which is rather slow. So what you need to do is you need to make sure that you, first of all, have your images in line. You know what you're going to label next. If you know that, then you can, of course, compute these things in advance. And so when the user loads the image, then you already know the image embedding, and you can do the decoding of the masks fast. So that's another thing we care a lot about. And then, of course, all the UX design around having all these things work properly. And I think actually the slide you had, now I'm doing what I'm not allowed to do in slides, right? You can never skip fast. Anyway, so I think this actually reflects pretty well what you'll be able to do in our editor today. So you can use this magic wand, and then you just, exactly as we discussed, add a key point to the object you want to annotate, and then you get the masks. Yeah, I hope that answered the question.
I think that was a great walkthrough. Maybe just to kind of round things out here, go back on the slide around the resources we're making available, and just going through each of them and how we are sharing them afterwards. And then I think we can wrap up the webinar, and we'll be sharing the recording afterwards along with these slides and resources. But a quick overview of like what they actually are would be, I think, helpful to the audience.
Yeah, definitely. So the first one is what I've been showing already. So that's exactly this notebook. All the code for loading the models, running predictions. The second one does the exact same thing, but it's automated around Encord Active projects. So if you have an Encord Active project, you can, with one line of code, you can run Grounding-DINO and SAM on the entire data set. You can get a file that you can import into Encord Active, and then you can actually see the model performance on your specific project. So that's the second one. Of course, the slides are going to be shared. Then there are 3 different blog posts that we have on our blog that goes into more details about what is SAM actually. How did we marry SAM and Grounding-DINO? So this is very similar to what I've been talking about today. And there's also a couple of pretty cool insights about Dino v2 in this other blog post.
Excellent. Thank you so much for your time, Frederick, and thank you everyone who listened in. We are Encord. Feel free to reach out if you don't know us already. Always happy to chat about computer vision, AI in general. Again, we'll be sharing the recording and the resources here after the call, so you can play around with it on your own time. But apart from that, really appreciate you all showing up, and we will hopefully see you again soon.